Okay, continuing from last time, let's put these definitions into context with a coin toss. So we'll always have some kind of experiment where we get one outcome. So let's say in this experiment, we're flipping a coin once. The possible outcomes are heads or tails, so this is the sample space. An event is a subset of a sample space. In this case, the options are pretty limited. But now let's do a different experiment where we toss a coin 3 times. Each outcome can be written as a vector, so the sample space is this. Order matters here, by the way. This is a more concise way to write it using the Cartesian product. Let's look at some events in this sample space. All 3 tosses land on the same side, an odd number of heads appear, or the event that one of these 3 happens. It doesn't have to be some fancy rule. Another experiment is picking a card from a standard deck. There's 52 possible outcomes with this as a sample space. Here's some possible events. Selecting a queen, selecting a red picture card, the union of these 2, a red picture card which is not a queen, so we have to take all the stuff that's in A1 out of A2. Another experiment is throwing a dart at a dartboard. Say the dartboard has a radius of 9 inches. The equation is this, and our outcomes can be 2D vectors where they fall within this circle. An event of this could be hitting the bullseye. Probability distribution. It's a function that assigns a number 0 to 1 to each event in the sample space. It says how likely the event is to occur. So here's some rules. We already said the 0 to 1 thing. P of the empty set is 0. You can't do an experiment and then nothing happens. And P of omega is 1. You have to get something in the sample space. For a finite or infinite sequence of pairwise disjoint events, we have this. This means that for a bunch of sets that don't overlap, to find the probability of any one of them happening, you add up each of their individual probabilities. A sample space is discrete if it's finite or countable. Let's say we have a discrete sample space. The probability of each event is the sum of the outcomes in the event. So for the coin toss, the probability of the event of getting an odd number of heads would be the sum of each of these outcomes. Part B says if we assign a non-negative number to each outcome in the sample space such that they all add up to 1, then we can define the probability distribution by setting P of A to be the sum of all the outcomes in A for all events A in omega. These look pretty similar, but part A is about how you compute the probability of an event, and part B says how you can build a probability distribution from scratch by assigning probabilities to each outcome such that they sum up to 1. Uniform distributions. Okay, let's say we have a finite set omega. A uniform distribution on omega is the function P, for which you can compute the probability of any event by dividing the size of the event by the size of a sample space. So for example with cards, let's say an event is we pick a queen. There's 4 queens and 52 cards in total, so the probability of picking a queen is 4 over 52. Another event could be picking a red picture card, so the probability for that is 6 over 52. So a uniform distribution is one where each outcome is equally likely to occur. Non-uniform distributions. Okay, straight into an example with flipping a coin. Let's set the probability of tails to be between 0 and 1, and the probability of heads to be 1 minus P. So when we add up the outcomes, we get 1. So now we built a probability distribution from scratch, satisfying all the rules. So if P is not half, then the distribution isn't uniform. It's a biased coin. Another example is picking a letter at random from the word statistics. So the sample space is this. Since we're picking at random, we're doing a uniform distribution on the letters. So we have an equal likelihood of choosing any letter, which is 1 in 10. But when we look at the probability of actually getting each letter, it's this. So it's a non-uniform distribution on the sample space.